announcement. So it might come as a happy surprise to you that there's no homework 6. There are many reasons for this. The first was that we are actually running really late on grading. I don't know why this is happening, but this was the main reason that we haven't yet graded homework 4, and I think many people are unhappy that grades are not being out quickly. And also, I guess it's the end of semester too, so everyone is happy. But meanwhile, so I've also, so I saw that there are at least 7 people who have not submitted the previous homework. So it is a bit unfortunate because they will lose a lot of points. So I plan to give out something, some kind of a make-up homework. So it will have problems from various topics. They will be out tomorrow. And the way this will work is that if you score, so this will replace your least homework. Okay, so unless this is lower than the least, in which case nothing will happen. but that's the idea. Okay, so yeah.
In another course, we have something like we drop the least score.
So this is equivalent to that in some sense, right? So it's just that this is not going to test the most recent topics. It's just going to be more of an overall thing. Okay. So yeah, so that's the thing. Yeah.
What about the solutions of the previous homeworks?
Yeah, so today, somebody wrote me a very emotional email. So I put up 2 homeworks yesterday, and they're on this discussion. And I'm in the process of writing. Actually, I had emailed you guys a couple of weeks ago, but no one did anything. So I started doing it myself.
Okay.
So I will do it. So I have some time tomorrow, so I'll write maybe 3 and 4 also. Okay, so yeah, anyway, so, but this one, I would say all of you should look at it, especially if you have concerns. Okay, so many people seem to have concerns. So the grading will be pretty relaxed, but still it is normal to have concerns, so you can take advantage of this. So, yeah.
But when you say grading is really relaxed, what is that?
Yeah, so no, I mean,
in your class?
So this is only relative to typical undergrad courses where you expect 10% of people to get an A and so on, right? So I think usually in undergrad classes you have a very fixed set of things. In grad classes, usually what happens is that maybe 30-40% of the class will get an A. Okay, so in that sense, it is more relaxed. So yeah, and at least 50% of the class will probably get A- or above. So that's usually how it works. Okay. So, but yes, there will obviously be some drop off, but it will just be that it's much more relaxed than in typical undergrad classes. Okay, so this is the thing, and yeah, all right. So also I have a few slides at the end. These are basically recap slides from what we did last time about the project. Okay, so let's do that. If you remind me 5 minutes before the end of the class, I will get to that. All right. So what have we been looking at, right? So we've been looking at this whole notion of you have a set of linear equalities and you want to prove infeasibility. Right? So this is one thing we looked at, and you have a bunch of inequalities, and we said that a general way to prove infeasibility of this system of equations is to show that they derive some contradiction. Okay? And we said that this is actually a complete way in the sense that for any system of infeasible equations, you can prove it this way. Okay, so this is something we saw last time. And by manipulate, we just mean taking linear combinations. And we also saw something similar about inequalities. Okay, so we said if you have a system of linear inequalities, you can again manipulate them in the sense you take linear combinations of them. Here you've got to be a bit more careful. You have to take, if you have all less than or equal to this, then you can only multiply inequalities by non-negative numbers. And then you get some contradiction of the form 0 less than -1, something like this. And what we saw last time is that this is equivalent to being able to have a proof like this is equivalent to the fact that this system is infeasible. And this we said is called this kind of a theorem. This forms the basis for what's called duality. Okay. And basically the reason we call it the dual is because once you have this theorem, you can write down the question of infeasibility as another system. Okay. So you can say, suppose you have one linear system of inequalities and you want to show that this is infeasible. Okay, so you can come up with a new system. Okay. So do you guys remember, so how did we derive this new system? If you remember.
Well, I think you multiply all of the equations in system 1 by vector or by the y's.
By the y's.
Yeah.
Yeah, excellent. So this is how we did it. So what we did was we basically wanted to do something like this, right? So we wanted to manipulate these inequalities, and the way you do it is you multiply this by y1, this by y2, this by y3. And we want to deduce 0 identically equal to 0 is less than or equal to minus 1. Okay, so that means the coefficient of x1 has to be 0, coefficient of x2 is 0, x3 is 0, and you have the right hand side to be equal to minus 1. Okay, so this is how we got this new program. And we saw this very nice, we didn't prove this statement for inequalities, but we said that it is true. So basically what we said is, there exists a feasible solution to this system 1 if and only if there is no feasible solution to system 2. And since it's an if and only if, it's also vice versa. Okay, so if you can find a solution to that, then it means this is infeasible. So this is why this is called duality, because you have these two systems of inequalities and they are duals of each other in this sense. Okay, and so this was for showing feasibility. Okay, so then we said, okay, so we have what if you have a linear program? Okay, so here you have a maximization problem subject to a bunch of constraints. Right, so this is a linear program, and we said that you can imagine trying to manipulate these constraints. Okay, which means basically you multiply this by y1, y2, y3 as before. And you try to deduce the condition that x1 plus x3 is smaller than or equal to something. Okay. So x1 plus x3 is your objective. Okay. So that's the one that you want to maximize. And you want to deduce the fact that x1 plus x3 is smaller than or equal to some z, which is like saying the maximum cannot ever be bigger than z. Okay. So that's how we said you can look at, this is one easy way to write down the dual. Okay, so you multiply these by this, and then, so if we need to deduce x1 plus x3 less than or equal to z, then your coefficient of x1, when you do this, which is y1, it should be equal to 1. Coefficient of x2 must be 0. Coefficient of x3 should be equal to 1. And we want to minimize the right hand side. Okay, so any questions about this? So this is actually a very crucial notion. So this is how you typically, so yeah, often people come up with some mechanical ways of writing down the dual, but this is a very easy way to remember, very easy way to derive it. Okay, so imagine you're trying to prove that the objective here cannot be bigger than something else, than some number, and you want to minimize that number. So that's how you should think of this. The questions?
What happens to the inequalities if you transform to the dual?
Yeah, so the only inequality that remains are these yi is bigger than or equal to 0. So the others are actually equalities. Now, any linear program, you can actually write it like that. Okay, so even this can be written in that form where you have a bunch of equalities and a bunch of non-negativities. Okay, so do you see why actually? Maybe it's not actually so complicated. So can you see how you can write any, even the left side, something that looks like the right side? You have a bunch of equalities and bunch of bigger than or equal to zeros. So if you haven't seen this, it's a bit tricky to come up with it, but what you can do is you can imagine introducing new variables here which are called slack variables. Okay, so imagine for every constraint I have plus s1, plus s2, plus s3, and then I can put equal to 2, equal to minus 1 and so on, and I just insist that s1, s2, s3 are bigger than or equal to 0. Okay. So this is an equivalent way to write this linear program. So in some sense, this is actually no less general than any other linear program. So it looks simpler than this, but it's actually basically the same. Yeah, so that's a good point. But yeah. Is there any other questions? Okay, so did you have a question? Alright, so let's then move on to, I see, let me formally state this duality theorem. Right? So this is, so this one, if we call this LP1, that is LP2, then the duality theorem basically says that if LP1 is feasible, okay, in the sense that there exists some feasible solution, and the optimum is bounded, so this is important, then there is a feasible solution to the dual and both the optima are equal. And the important thing to notice is that one is a maximization problem and the other is a minimization problem. And in some sense, the way this works is if you have, so this is, let's say, the real line going up, and you have various feasible solutions to LP1, okay, and they will have some optimum. This is opt of LP1. Then there will be various feasible solutions to LP2, and each feasible solution will actually be bigger than the opt. Okay. And the opt of these two coincide. Okay, so this is equal to also opt of LP2. Okay, so this is what we saw last time. And we said that even this observation that every feasible solution to LP2 is an upper bound on the primal optimum is sometimes useful. Okay. So sometimes when you're coming up with some algorithm, you might say, here's a dual solution, and I'm doing well with respect to that dual solution. Okay, so yeah, let's not get into that, but you can see why this is useful, right? Because if there's an optimization problem, it's nice to always have a sense of what the optimum is going to be, okay, or some upper bound on the optimum. Okay, so that's what it is. Alright, so what we're going to see today is some non-trivial application of this duality theorem. Okay, so this as such basically says, you know, for any linear program you can write down this dual and the values of these two are equal, right? And they seem to capture slightly different aspects. Okay, so let's see how this is useful. Okay, so the first example is something that we've seen before. Okay, so we go back to the max flow problem. Okay, so here what's the problem? You have a directed graph and you have a source and a sink, and we want to send as much flow as possible from S to T. And every edge has a capacity C of E. couple of lectures before we saw that you can write this as a linear program. Right, so what were the variables we said we could choose? So what defines a flow? The flows on the edge. Yeah. Well, the capacities are given to you, right? So it has nothing to do with what the actual flow is. So the actual flow on every edge are basically what you have to figure out. So you could say for every edge there is this Fe value, and you have flow conservation as a constraint, and at every node. Then you have Fe bigger than or equal to 0, and you want to maximize. So what's the objective if you write it this way?
The flow outgoing array, so incoming at T.
Yeah, so is that point clear? So basically for every other vertex, the net flow into this vertex is 0. Okay. So what we actually is, so the value of the flow is basically what originates from S. Okay, so that's the quantity that we want to maximize. Okay, some E out of S F. Okay. So this is a perfectly valid way to write down the flow linear program, and you can solve it, you will get the maximum flow. Right? But so today I'm going to write it down in a slightly different way. Okay. I'm going to write down a formulation that has exponential size. Okay, but it turns out that it's going to be useful. So that's what we will see today. Okay, so this actually, if you think about it, it's a more natural way of stating the flow problem. Okay, because a flow is basically a collection of paths that go from S to T. Every path has a certain amount of flow on it. Okay. And so you can also try to cast this problem as you have a variable for every possible path. Okay, so these paths could share edges and so on. Okay, so this is supposed to be a path that shares some common thing with the other path. Okay. So I want to, so the broad goal is write a different and an easier LP for flow, for max flow. The way I want to do it is by having variables, some variable f sub p for every path. From S to T. Okay. So are the variables clear? So you could have potentially exponentially many variables. Okay, so you could have one for every possible path. So I think I have a graph. Yeah, I have a graph here. So if you have a graph like this, and if this is S and T, then you'll have one variable for, let's say, this path, another variable for this path, and so on. Okay, so these two paths share one edge. Okay, and that's fine. Okay. So this is the kind of a linear program that I want to consider. So now so these are the variables for the linear program. So now, what do I now need to maximize? If these are the variables that I keep track of. Yeah, so basically what we want to maximize is the total flow, right? So think of these paths as capturing all possible ways of flowing, of having a flow from S to T, right? So there are many paths across which you could have a flow. And for each of these paths you have a variable. So the total flow is simply the sum of all these f sub p's. So it's sum over all p, which is the set of paths from S to T, of f sub p. And of course you have to constrain that each f sub p is bigger than or equal to 0, because you can't have a negative flow. And what other constraints should you have? Like you have some variable that tells you the flow along any path, right? So what other constraints do we have on a flow?
If you got an edge, the flow on that can never be more than its capacity.
Yeah, so we need capacity constraints, right? So that's the important thing in a flow. So how do you capture a capacity constraint? You have various paths that could potentially use a single edge. Okay, so you have a single edge, and this is one path, and then maybe there's a different path that uses this edge, and so on. Sum of all such flows, okay, so this will have some flow fp1 on it, this will have some flow fp2 on it. But fp1 plus fp2 should be smaller than or equal to the capacity of this edge E. Right? So this is true. If I fix an edge, look at all the p's that use, paths p that use that edge. The sum of the f value should be smaller than or equal to the capacity. Okay. So this is the other constraint. Sum over all edges, sum over all paths that contain some edge E. Okay. So for every E, f sub p is smaller than or equal to C of P. Okay. So is this point clear? So this is just the capacity constraint in these new variables. So do you have a question? Is this notion of different variables clear, by the way? Okay. So you have one variable for every path. So that's how you should remember it. And this is the total number, this is the total amount of flow. And for every edge, you have the sum of the flows on all paths that contain that edge is small. So this is, let me write it right here. So this is the linear program that we are considering. So this is, you want to maximize the sum, the total flow, right? So it's sum of all the flow values. And for every edge, you have this capacity. So now you can write down the dual for this linear program, right? So this is just a simple linear program. So this one, if you want, you can write this as minus fp less than or equal to 0. So how would you write the dual for this? So I said the way you write a dual is for every constraint you have some y. Okay. So here constraints, the first kind of constraints are indexed by the edges. Right? For every edge there is one constraint. So let's say I have the variable y sub e. Actually, let me call it x sub e because that's what I am using later. So let's call this x sub e. Okay, so x sub e is the variable for that constraint. And you could also potentially have constraints for this. Right? So for every p, you could have some y sub p. Okay, so I'm going to call this yp. And you can now imagine adding them all up. Okay. And so if I write down the dual, what it will be, so what is the objective in the dual? Remember, the goal in the dual is to try to prove that the primal objective is smaller than or equal to something, right? And if I had these guys and if I added these constraints up, okay, the primal objective has coefficient of 1 for every FP. Right? So the primal variables are these FPs, and every FP has a coefficient 1. Okay, so after I manipulate these things, what I should get is the total coefficient of each FP has to be equal to 1. Okay. So let me write down those constraints. Okay, so I'll just write total coefficient of each FP for all parts P. Okay, and what is the coefficient of each FP? So if I add
All the reduce
yeah, so you'll have XE for every X that is in that path, right? Because that edge will contribute. Okay, so this, so maybe you should, if it helps, you should probably write down an explicit graph and see how this works. But if you think about it a little, you'll realize that the coefficient of an FP will be basically the sum of all the edges XE that are in that path. So that will be easy to see. So you basically get sum over E in P XE. And then you have this last thing, right? So you have this Y minus YP that just comes up. So minus YP is equal to 1. Okay. So this is very easy, this shows up. And this is true for all paths P. And you have XE and YP bigger than or equal to 0. Okay. So these are the constraints in your dual. And now what's the objective value? Yeah, so basically you just have XE times the C of E's adding up, right? So these are just 0 because the YP times 0 is just 0. Okay. So all I'm doing is I'm imagining multiplying every equation of this kind by XE, okay, and adding equations of this kind by YP and adding up. And I'm just looking at what the right hand side is and what the left hand side has to be. And so this also is very simple. So this comes out to be sum over E, C of E times X. So this is what you want to minimize, subject to this. So now we can. So this is a variable. This is again a linear program. Okay, firstly, this is a minimization linear program. What's the number of variables in this program on the right? Yeah, so what are all the variables actually? So they're just the XE's and the YP's. Right, so these are all the variables that are there. Okay. And there are m such, the number of XE's is just the number of edges. And the number of Y's is just the number of, there's one Y for every path. Okay, so number of paths from S to T. So this is what this is. But I claim that you can actually simplify this. So can you get rid of these YP variables? Because the way they show up is actually in a very easy way, right? So they never show up in the objective. Okay, so the YPs never show up in the objective, and they only show up here. And you know that YP is bigger than or equal to C. So is there an easy way to get rid of the YP variables? Actually, let me ask an easier question. So, for every YP, how many constraints does it show up in the dual? Okay, so is the question clear? I'm asking, so the dual has one constraint for every path. And I'm just asking, if I fix one P, and I ask how many equations does y sub p show up in? So any two. Which ones?
The last two.
Yeah, so it's this one, of course. Yp has to be bigger than or equal to 0. And for that p, there would have been one equation. And in that equation, it would have shown up. So these are the only two equations, two constraints in which yp shows up. And for all other p's, there will be different y's. And that makes it very simple, right? Because what if so what if I just replace this e belonging to p x e less than or equal to 1? Okay, so I want to replace this constraint. It's bigger than or equal to 1. I claim that removing yp altogether and replacing this constraint with this maintains the value of this linear product. So do you guys all see this? So basically what I'm saying is, so this is exactly the opposite of what I did when I spoke about these slack variables. Okay. So earlier what I said was, if you have an inequality, if I have some x less than or equal to c, I said that I could replace this by having a condition that x plus s is equal to c and s bigger than or equal to 0. Okay. I said that any constraint of this form can be replaced with two constraints of this form. Okay. And it's exactly equivalent. Now I'm planning to do the opposite. Okay. So I have constraints exactly of that form. Okay. So I have this minus p, and since it's minus, the sign of the inequality will become bigger than or equal to. So questions about this? So I'm saying that I'm trying to go in this other direction. Okay. I'm trying to say that having a constraint like sum of xc minus yp equal to 1 and yp bigger than or equal to 0 is exactly the same. It's just having this constraint. This is very nice because now your number of variables in this in the dual is actually very small. Okay, so it's just the number of edges. Okay, so all these variables went away. Okay, so I will pause for a bit and see if you guys have any questions. Yeah.
Shouldn't it be the other way around? Xc less than equal to 1? According to what you recommend.
Yeah, so in what I wrote there, you had x plus s bigger than is equal to c, right? So here it's like x minus s equal to c. Okay. So yeah, and s is bigger than or equal to 0. So basically it's like saying x is bigger than or equal to 0. So this is an algebraic trick, but what we have seen is that this dual is exactly equivalent to not having the yp's and just having these constraints. So once you make that observation, you have a pretty simple formulation for the dual. Okay. So it just becomes, you have variables xe for every edge, okay, and you want to minimize the sum over e cexe, okay, so this is your objective, and you have this constraint that for every path, sum over edges in the path xe is at least 1, okay, and this came from this trick that we did. And of course you have every xe is bigger than or equal to 0, because this you always had. So now the dual is relatively simple. It has a lot of constraints. So the number of constraints is still the number of paths. Okay, but number of variables is small. So it's just size, it's just the number of edges. And this is one thing that kind of happens a lot of times. So you start off with a program that has a lot of variables and a few constraints, and the dual will have the opposite behavior. Okay, so it has lots of constraints, but it has very few variables. Alright, so now okay, so this is fine, right? So this is just some linear, this is another linear program, and the duality theorem that we saw before basically tells us that the optimum of this is equal to the optimum of the previous LP, okay, which is equal to the max flow. So that's what it tells us. But but let's try to interpret this linear program. So what is this saying, right? So this is like saying for every edge, okay, so remember you have some directed graph. What this is asking is, for every edge E, you want to come up with some variable xe that's non-zero. So you can, in some sense, think of these xe's as a length for every edge. Length is different from a capacity. Okay, so length as such has nothing to do with the capacity. And what we are saying is, if I look at any path from S to D, the total length of that path, okay, which is the sum of the edges, is bigger than or equal to 1. Okay, so that's what we mean. So this is how you can sometimes interpret this dual. Okay, so you want, so an example could be you have 0.1, 0.4, 0.5, and these have to add up to 1, and so also these could be some numbers that add up to 1. And if you had a different path like this, then you could have some other values. Okay, so these paths share edges and so forth. So this is the dual formulation. If you think about it, it's relatively easy, right? So every variable for every edge, give some edge length, and length of any path from S to T is at least 1. Okay, so this is a simple interpretation. So now, what I want you to think about is, suppose I consider a 0-1 solution to the dual. Okay, so here I allowed xe to be anything, right? So xe is any fractional value. Okay. Suppose I tell you that xe is actually either 0 or 1. Okay. So what does it mean? How do you now interpret this constraint? Yeah, so basically what this says is xe being 0, 1 means there are some edges that have xe 1 and the rest that are 0. Right, that's what it means. So maybe you have something. We are saying that on every path there is at least one xe value that's at least 1. Okay, so otherwise this constraint will not be satisfied. And that's like saying along any path there has to be one edge that's selected. Okay. And so what is this? Do you guys see what this would be?
Like a cut from.
Yeah, so this is exactly a cut problem. Okay, so because basically that's the definition of a cut, right? So a cut is a collection of edges whose removal disconnects S and T, okay, which means there is no remaining path from S to T. Okay, so if you had a 0-1 solution to this integer to this linear program, then it exactly captures the cut problem. Okay, so this is exactly captures the min cut problem. Okay, because the objective is to minimize the sum of the capacities of the edges that you cut. So let me write this down. Okay, so observation. The one edges from cut. From cut from S. Okay, so this therefore minimization problem captures min cut. So this is assuming you had these constraints. So this is alright. So this is nice, right? So you have a easy interpretation of this if you have 0, 1. So now what happens if you don't have these, right? So what happens if you just remove these? You just had xc bigger than or equal to 0. Okay, so let's see that. And yeah, so one thing to note is that this observation implies that the optimum value for the dual is smaller than or equal to the value of the min cut. Okay, so do you guys all see this? And this is actually for the same reason we saw last time. Okay, so basically if I had additional constraints xc belong to 0, 1, then I said that this exactly captures the min cut problem. Okay. And if I remove these constraints, then the objective value can only be smaller, right? Because there's a minimization problem. So this is what gives this claim that the optimum for the dual is actually smaller than or equal to the value of the min cut. So let's now try to argue that it cannot. So the question now that we want to answer is, can it be strictly smaller? Okay. So can optimum value of the dual be strictly smaller than the value of the min cut? Okay, and we are going to claim that no. In fact, so the theorem that we'll show is that the optimum of the dual is equal to the value of the min cut. And we're going to show it the way we normally do, that is, we'll show that there exists a cut with value smaller than or equal to the opt of the dual. And if you combine this with the previous observation that opt of dual is smaller than or equal to the min cut, then you get that that both are equal. Okay, so this is the usual way of showing it. Okay, so this will be the claim that we will show. Okay, so that there exists a cut. So what we'll do is, so this is a more tricky example of a rounding algorithm. Okay, so this is the kind that we saw last time. Basically what we will do is, we'll start with any feasible fractional solution, xe, okay, and we'll show that there is actually a cut whose cost is at most the objective value of that fractional solution. Okay. So this will be the steps. So the sequence of steps will be consider any feasible fractional solution xe, then we'll come up with a cut S bar such that value of cut is smaller than or equal to sum over E COT. Okay, so this is what we're going to do. Okay, so this is nothing, and then so this is what we need to show. Okay, so you consider any feasible fraction solution xe. We'll come up with a good cut. So is the method clear? Okay, so and what we are proving and so forth. Any questions? So let's now show this. Okay, so the idea is actually a bit tricky. Okay, so the way we do it is by considering what are called distance cuts. Okay, so remember I told you any feasible solution to this, the xe's can be interpreted as lengths. Okay, which means that I can define a notion of distance using these lengths. So what I could say is, okay, so I look at any edge. So this edge could have xe equals 0.1. This edge could have xe equals 0.4. This could have 0.2 and so on. Okay, so I hope these are visible. So these are the xe values. I said xe's are interpreted as distances, as lengths, right? So the idea is to look at this source vertex S and look at all the nodes that are at a distance of some threshold theta from it. Okay, so and the distance is measured as the shortest distance according to these xe's. Okay, so the xe's, so if you have S over here and you had 0.1, 0.2, 6 or something. And if your theta is something like 0.2, then the set of nodes at a distance smaller than or equal to theta are this guy, this and this, right? And also S itself. So this is what I mean by S sub theta. Okay, so S sub theta is the set of vertices that are at a distance smaller than or equal to theta from the source S. Okay, so this is how I define these what are called distance cuts. This is actually a very powerful thing when people consider cut problems, this notion of a distance cut. Okay, so it's so I thought this is a very simple way to illustrate that. Okay, but is the definition of S sub theta clear? Okay, so this is an example. If theta is 0.2, then the distance to this guy is 0.2, distance to this is also 0.2, so on. Okay, so you could have multiple paths, like this could be 0.1, doesn't matter. Okay, so that's what this is in terms of shortest path. Okay. Yeah, people seem to be slowly. It reminds me of this. So Seinfeld has this comedians in cars show, right? So there's some guy who shows up and says, apparently he was doing stand-up, and and everybody left the room and after hopefully that doesn't happen. Alright, so anyway, so this is how you define S sub theta. This is all nodes that are distance smaller than or equal to theta from the source. Alright, so yeah. So now what we're going to claim is that there is some value for theta for which S sub theta, the cut S sub theta has the property that we want. Okay? So remember, we are looking to come up with a cut such that the value of the cut is smaller than the cost of this linear program solution. Right? So we are going to show that one of the S sub thetas has a value that is smaller than or equal to this. Okay? And the way we will show it is by actually showing this more interesting claim. So and once I write it down, this will. So what we will claim is that the integral from 0 to 1 of the size of this cut E of S theta bar. So this d theta is smaller than or equal to whatever we have on the left side. Okay, so sum over E . Okay, and size of the cut, just remember, is equal to sum of the weighted sum of all the edges, right? So it's sum over all edges, sum over all E in this cut of C of E, right? So by size, I just wrote it down because by size I don't mean literally the number of edges, it's the weighted sum of the edges. That's the quantity we are interested in, right? So in any min cut and so on, we are interested in the weighted min. Okay. So this is what we mean, and so this is what we are going to show. Okay. So I'm going to show that, think of this as some kind of an average over all thetas. Right, so the integral of a quantity between 0 and 1 is essentially like the average value of this quantity. Right, so what I am showing is that the average value of this E sub theta is actually smaller than or equal to what we want. That means there has to exist a theta for which it's small. Okay, and this implies that there exists a theta such that E of S theta bar is less than equal to . Okay, so is this claim here that, so what I'm saying is, so this is actually a very cute way of showing that there exists some good theta, right? So if I want to show that I have this function of theta and I want to show that at some point it takes a value that is small. Okay, so this is like showing integral of this function from 0 to 1 is small, and that means that there is some point at which it's small. Okay, so this can't always be bigger than some threshold and have the integral value being smaller than. Okay. So that's what is happening here. Okay, so this is a typical averaging argument. Okay, so this is what we're going to show, and the way we are going to show it is actually, now that I wrote this down, it's actually relatively easy to analyze. Okay. The way we are going to analyze it is by looking at every edge. Okay. So let's analyze this. Okay, so let's analyze sum over 0 through 1. Integral over 0 through 1. The weighted sum of S theta okay. So
E of S theta bar is basically the edges between those two sets,
Yes. Yeah, so it's it's a set of all edges between s theta and the complement of s theta. Okay, so and s theta is defined like this. Okay, all vertices that are at a distance at most theta. And the way I want to analyze this again is by saying, so the way you should think about this process is that suppose I start with s and suppose theta is 0. Okay? Suppose all the xe values are at least some very small positive quantity. If theta is 0, right, so then you would assume that, you would guess that s sub theta is just this vertex s. Now slowly as you increase theta, more and more vertices will start coming into s sub theta. Okay, so the cut will keep changing. Right, so this is essentially what a breadth first search also does. Okay, so if you did a breadth first search, this is exactly how this would slowly progress. Okay, so this cut is basically the frontier that you see in breadth first search. Okay, so actually in Dijkstra, because it's a weighted graph. Okay, so if you think about what the contribution of each edge is to this integral. Okay, so suppose I have some edge out here, right? So this is some edge E and this is UV. Okay. So what is the contribution of this edge? So let's say its capacity C of E to this integral. Can we actually come up with a number? And suppose I tell you that distance of V to S is d sub V, distance of U to S is d sub U, okay, and assume d sub U is smaller than 50. Okay, so is the question clear? What I'm asking is, so for every theta, this is just a sum of the edges, right? Sum of the edges that go between the cut s theta and s theta complement. Okay. Now what I'm asking is, if I fix one edge, what is its contribution to the integral? Okay. So in particular, for what values of theta will this s show up in this quantity? Is the question clear? So you have this edge, right? So there is some particular edge. Okay. Now, if this theta is bigger than dV, okay, so let's consider the case theta is let's consider the case theta is smaller than du. So in this case, neither u nor v will be included in s sub theta, right? Because s sub theta is actually smaller than both theta is smaller than both du and dv. Okay, so s sub theta will not include either of these. Okay, so the edge will not be in the cut. Okay, and the same will be true when theta is more than dv, which is the bigger of the two. Okay, in this case, s theta will include both u and v. Okay, which is why this won't show up in the cut. So this analysis is takes a little bit of time to understand, but it's actually extremely simple. Okay, so it's very beautiful once you get it. Okay, so I would advise you to think about this. Okay, so it turns out that this edge shows up in this E term exactly when theta lies between du and dv. Okay, so So if I think of theta as going from 0 through 1, then there will be a du somewhere, it's a dv somewhere. Here the edge doesn't show up in the summation, in this quantity. Here the edge doesn't show up. It's exactly in this interval that it shows up. Okay. And when it does, it always contributes the value c of e to the summation. Okay, because that's the size of this edge, that's the capacity of this edge. Okay, because this is just the sum of the capacities of edges that go from s theta to s theta bar. So think about it for a bit. So this is one of these things that you better if you figure this out for yourself. Okay, so turns out that you can write this as sum over all edges E equals uv c of e times d of v minus d of u. So, dv minus d. So here I am assuming that dv is bigger than d. Okay, so otherwise it's just the absolute value. Okay, so let me just for correctness write it like this. Okay, so this is actually the reason we went to the integral in the first place. Okay, so if you think about how one would have come up with such an argument, so one way to look at this summation is as this integral, and that's why you go to this averaging argument. Okay, so yeah. For those of you who wonder how someone could have come up with such a proof. Okay. So it's because of this. So this integral is exactly this, and now I claim that this value is smaller than or equal to xe. Okay, so why is that? So this is actually a very simple claim, even if you haven't followed anything so far. So what it's saying is, I look at s, and I look at the distance to v, okay, and I look at the distance to u, that's du. The difference between these two is always smaller than or equal to x sub e. Note that the distances are defined by the x-axis, right? So by the x's. Okay, so this is actually true for any shortest path, right? Because if I can go to u at a cost du, okay, and from there's an edge of cost x sub e, then dv is always less than or equal to du plus xe. Okay, so in particular, dv is always dv minus du is always less than or equal to xe. Okay. So again, think about this for a bit, and you might say, can du be much more negative? Okay, but it doesn't matter because our edges are all directed. So you can work this out. Okay, so it turns out that this integral is always smaller than or equal to sum over e c of x. And this is basically how the proof works. Okay, so you show that you look at this integral and you show that this is smaller than or equal to c of exe by doing this clever argument. And what this implies is that there exists a theta such that the cut is small. And that's basically the proof. Okay, so yeah, if you haven't followed it, it's fine. This is a little bit of a tricky proof, so go back and watch the video, I guess. Alright, so yes, so let me end this part. Okay, and so what we've essentially done is we've given an alternate proof of the max flow min cut theorem. Right, because we said that by duality, the optimum of the primal is equal to the optimum of the dual. And then you have that optimum of the dual is equal to the value of the min cut. Okay. this is what this previous proof showed, that the optimum of the dual is exactly equal to the value of the min cut. And this is another, I guess it's somewhat simpler, at least if you agree with LP duality and you don't have to prove it, this is actually a simpler proof of the fact that max flow is equal to the min cut. Okay. So, yeah, so this is just one thing that I wanted to say. Okay. And so I wanted to, before we go on, I wanted to just do a quick summary of linear programs. Okay, so what we did so far is we said that linear programs are useful to capture various continuous optimization problems. Okay, so these are things like flows and matchings. We saw lots of these kind of problems. Okay, they are used for scheduling and various other things. Okay, and we said that they are also useful for discrete optimization problems. Okay. So as such, linear programs don't allow you to have any integrality constraints, but often you can do some kind of rounding. Okay. And we've seen some good examples of rounding. So for vertex cover, we said just rounding up things that are bigger than half works. Okay, gives a good enough solution. And today we saw an example where we did a non-trivial rounding. Okay, so you can think of what we did here as starting with some fractional solution and changing some of the x's to 0 and some others to 1. Okay, so you can think of this as rounding. Okay, so I guess you guys can figure that out. And then we said that, and then we introduced duality, this notion of proving that things are infeasible and how that leads to this whole nice theory of duality. Okay? And then we said that if you have a linear program, you can actually bound the optimum value pretty easily sometimes. Okay? And there are also some very nice applications of this. So especially to this whole area of game theory and economics. Okay, so since I have a few minutes before 12, at 12 I want to get to the project, but I just wanted to give a sense of what kind of things and why you expect linear programs to even show up, right? So one of the kind of the important concepts in game theory is this notion of equilibrium. Okay? So how many of you have seen this picture, this notion of prisoner's dilemma? Okay, so most of you at least know, so I can quickly go through. Okay, so it's like you caught two people and you believe that one of them is guilty. Okay, and this is like a standard interrogation technique, I guess. So what they do is, so if one guy confesses and the other remains silent, okay, then the guy who confesses gets 0 years, and the guy who remains silent gets 20 years. Okay, so you figure that he's the guilty one. Okay, so that's the one on the right. Both of them confess, then they both get a fairly high, a moderately high thing. Okay, so I guess confess is not the right word, so this picture is not that great, but anyway, so yeah. And if both of them remain silent, then you don't have much of a charge, so you basically get 1 year of each. Okay, so each one gets 1 year. So what's interesting here is each player has two choices, right? So they can either do confess or they can either remain silent. Okay? And depending on what they do, it's not just what they do, depending on what they and the other guy does, the payoff is determined. Right? So if you look at the point from the point of view of this prisoner A, okay, so if he decides to remain silent, and the other guy was also cooperative, and the other guy also remains silent, then it's pretty good. He only gets 1 year. Okay? But now suppose this guy knew that the other guy was going to remain quiet. Then he could just be, evil and say and confess himself, and then he will go off happily with no prison sentence, and the other guy would be stuck for 20 years. Right? So this is kind of a bad solution. Okay? So it turns out that for this kind of a problem, there's no notion of an equilibrium in the sense that a player always has an incentive to deviate. Okay? So a player always has an incentive to deviate. Okay, so given so the way to think about it is, if he knows what the other guy is going to do, then they would actually change their the way they play. Okay, so that's what's called the incentive to deviate. Okay. And for any solution like this, you can actually you can consider the 4 cases, and you can convince yourself that player would always want to deviate. Okay. But it turns out that if you look at what are called mixed strategies, okay, where so it doesn't make that much sense in this case, but in this case you can think about every player as giving a set of probabilities, okay, and say that I'm going to confess with some probability, I'm going to remain silent with some other probability, and then you compute the expected payoff. So it turns out for these kind of what are called mixed strategies, there is always an equilibrium, okay, and an equilibrium basically means that at that equilibrium, neither of the players has an incentive to deviate. Okay. So this is not a very great example for, so you can't show this by using linear programs. But it turns out for this big class of problems that are called zero-sum games, you can actually show, and this is just a very simple consequence of linear programming duality. Okay, but it takes some while to set up all the notation and so forth, so I didn't want to get into this. Okay, so what I would just want to say is there are some generally interesting applications, and I'll try to put up some links to these kind of applications on the homepage. Okay, so this is actually a very powerful theorem. This is by von Neumann and Morgenstern, and they actually came up with the first kind of a study about formalizing economic behavior in games. Okay, so that book is still a classic. Okay, so there are a lot of expositions on it. Alright, so yeah, so now let's move to, so I just wanted to recap what I said earlier about the final project. Okay, so, and this is one thing I just wanted to stress again, is many of the papers that you guys picked are probably not very easy to read, so I would encourage you to look at other resources. Okay, so many of these papers have lecture notes and stuff, and they will usually be much easier to analyze than the actual paper, to understand than the actual paper. Okay. And yeah, so this is, yeah, as I said, it's just 2 pages, and you're supposed to have what they solve, basically what the problem they solve, and you should give some sense of why this is important. Okay. So, and you don't have to focus that much on the previous results if there are too many. Okay, just make sure you do maybe a 1/4 of a page on these. Okay. And yeah, so and as I said, you have to. So there are 2 aspects of most of these papers, right? One is they are important in the sense of the contribution they make is important. The other is they are important in a technical sense that they actually solve some difficult technical problem. Okay, so that's the other thing that you should emphasize. And of course, state the main result. Okay, so this is related to this, to the problem statement, in the sense that it will solve say something about this big problem statement. And if it's an algorithmic paper, then some outline of the algorithm. Okay? So some of the papers like primality testing have complicated algorithms. So in this case, I think you should just you should just talk about the main steps. Okay? And you can assume there are subroutines that do such and such. And again, the same is true for the proof. Okay? So it's you write down the main lemmas and the main structure of the proof. Assume all the details can be worked out. And yeah, so the outline of the proof is the tricky part, and it's good to give some rough idea and general statement of the main lemmas and why they imply the main lemma. And this part should take about 1 page. Okay. So this is what I would guess. The rest of the stuff together is about 1 page. Okay, so the algorithm maybe is 1/4 and the others are half. So that's the breakup I would expect. And yeah, so the main thing which I wanted to stress is that what you produce should be somewhat self-sufficient. Okay, so in the sense that if somebody just reads that, they should be able to understand, oh, what was that paper talking about? Okay, so that's this is one thing that I wanted to emphasize. Okay, so maybe they don't understand the full details, but they should at least know, okay, this is roughly what that paper was solving, this is roughly how they solved it. So that should be your objective. So you should have, the reader should understand.